Hello everyone, I'm Xiaowu from Leiden University Medical Center. Glad to be here to present our work on this year's challenge. Today my topic is ventricle segmentation via registration and multi-input modalities in cardiac magnetic resonance imaging from multi-disease, multi-view, and multi-center. The diagnosis of cardiac disease requires accurate segmentation of cardiac structures. Traditional manual segmentation method is time-consuming and labor-intensive. In recent years, CNN-based method has been achieved big success in cardiac segmentation. But the performance of CNN model will degrade if a treat model is applied directly on other unseeded sets from different centers and different vendors. Yes, the challenge aimed to build a method to segment the right ventricle using multi-center, multi-disease, and multi-view data. This challenge provides 360 cases in both short axis and long axis views from 4 different centers acquired with 3 vendors. As shown in Table 1, is set the normal subject. There are 5 pathologies in training dataset. 2 pathologies are not present in the training dataset but only in the validation and the testing dataset. In addition, only ED and ES phases in the training dataset are labeled. The most straightforward approach to solve this problem is to collect and annotate data from multiple centers, vendors, and patient pathologies. Tao used a large data set from different centers and different vendors to train a CNN model and achieve good generalization. Chen illustrated that applying data augmentation method on a single site, single scanner dataset could improve the performance on NC dataset across different sets or scanners. Based on those studies, we hypothesized that a large-scale pooling data from different domains could improve a model's performance on NC dataset. Additionally, in the conventional CNN models, the information derived from the neighboring images is usually ignored. In our work, we investigated several methods to generate more training data and get more features, including the use of image registration to propagate annotation mask to unlabeled faces, and also introducing the spatial and the temporal neighboring images to construct multi-channel 2D images to integrate more spatial temporal information for the segmentation. Because other phases from the same case have almost the same intensity distribution, hence we use intensity-based registration method to propagate the labels regarding the ED and the ES as a template. The progress is described in Figure 1. Given 3 phases, ED, ES, and unlabeled phases, the ED and ES are first registered to the unlabeled phase, generating 2 geometric transformation matrices named ESTF and EDTF. Then the transformation matrix with smaller norm will be used to propagate the mask. We designed 4 kinds of input modalities for the network, including spatial multi-channel 2D images, temporal multi-channel 2D images, single-channel 2D images, and the 3D volume. As illustrated in Figure 2, a short axis linear MI contains multiple slices and multiple phases. Images from the same slice level describe a cardiac cycle, whereas the image from the same phases describes the complete heart structures. In conventional method, each single channel 2D images are 3D volumes, with the whole images from the same phase is usually considered as the input of a network. Also, using single channel 2D images as the input could enlarge the training dataset. A 3D volume can provide more spatial information for the segmentation. As a compromise, a spatial stack and a temporal stack model as proposed in our previous work, can be used to build a multi-channel 2D images, which can provide some spatial and temporal information for the segmentation task. M&M-2 is a fully automatic medical image segmentation framework. M&M-2 was specially designed by investigating various data computation techniques and ranked first at the first edition of MMS Challenge. Hence, we introduced M&M as a baseline and built our method upon M&M-2. Other models in this study are based on a 2D network. The propagated data was used to pre-train the model, and the manually labeled data was applied to fine-tune the pre-trained network. The model achieving the best performance in short-axis view will be used as the pre-trained model for the long-axis view instead of using different input modalities. Table 2 shows a brief summary of training data size in short-axis view after combining the registration. The original dataset contains 323 volumes, 2,704 2D images with labeled annotation for training. When applying the registration approach to propagate the annotation masks, the data size increased. We first evaluated the performance of different networks with different input modalities in the short-axis view from the validation dataset. Then we compared the result in the long-axis view with and without pre-training from short-axis view. Table 3 shows that using 3D volume without registration process as the input, M&M-2 achieved a slight better dice than M&M, but yield worse half-stop distance. However, when the registration method is applied to generate more 3D volume data to pre-train M&M, it achieved the best performance with a dice of 0.922 and a half-stop distance of 9.472 mm. It also can be observed that the segmentation results derived from the two stack models, SMI and TMI, are better than that from SCI, which confirmed that SMI and TMI could provide more spatial and temporal information for the segmentation task. The results in long-axis view in Table 4 illustrate that the performance increased by 0.01 and 0.7 in terms of dice and half-stop distance as a result of transferring the pre-trained model from short-axis view to long-axis view. We chose the model with performance best in the validation data as the final model. We submitted our final model to the organizer and evaluated the performance online. Table 5 shows the details about our method on the testing date. In addition, there are two pathologies not present in the training date but only in the testing date. The results on those two pathologies reveal that our method could get good performance on NC pathology. We investigated label propagation and multiple input modalities to increase the robustness in right ventricle segmentation from multi-disease, multi-view, and multi-centers MR data. To enlarge the training dataset, we exploited the use of image registration to propagate annotation mask to unlabeled faces. We further investigated the effect of using different input modalities, including 3D volumes, single-channel 2D image, spatial stack, and temporal stack. The results illustrate that spatial stack and temporal stack provide more information for the segmentation task, and using 3D volumes with label propagation could further improve the generalization ability in an NC dataset. Thank you for your attention.